This video has the goal of explaining in a simplified way how system dynamics can be used to represent a complex problem. Specifically, the Craig-Larman software development process simulation model would be explained, emphasizing on the factors affecting such process during the life cycle of the project. System dynamics is a language. It's a diagramming tool for representing the system dynamics language elements of a system. A simulation paradigm that allows us to appreciate the evolution of the elements of a system along time. And a decision support tool as well, since decision makers can use the information generated by the models to support decision making. In short, system dynamics is an approach that people can use to represent problems, to represent processes of the real life, but problems and processes which have the main feature of having a dynamic behavior. That is, processes and problems that change in time according to many variables and many environmental factors. For example, system dynamics can clearly represent populations, which increase or decrease in time according to many societal factors, or accumulations that occur in systems that may be in a wide variety of fields like chemistry, the health sector, or fluid mechanics, just to exemplify. But how can we work with system dynamics? In general, how do we use such approach? Well, there are general steps. First, it is important to identify all the elements involved in a problem or process and the relations among these elements. This is the identify causality step. For example, for the case of representing a population, the elements intervening would be, of course, the birth, the death, the birth rate per person, the contextual desired family size, the resources available per person, the life expectancy for this population, etc. And beyond identifying the elements, the connections should be built. So it is important to see how, for example, the more births there are, the biggest the population would be. On the other hand, the more deaths occur, the lower the population would be. But it is important to note as well the feedback dynamics in this representation, so that, for example, the higher the population is, the more births are expected to occur, and the higher the population, the higher the number of expected deaths is as well. Also, some fixed variables may be affecting some of the elements, such as a pre-established birth rate, which directly affects the births number. Also, the birth per person is affected by the desired family size, which you can see here, which is a contextual parameter, also related to the life expectancy of this population. But note that this expectancy is directly dependent on the available resources per person, and at the same time it is directly affecting the deaths that are occurring. And like this, you can identify many other possible relations. Another important aspect of system dynamics is identifying the feedback loops, which may be positive or negative. Positive in the case of reinforcement loops, or negative in the case of regulation loops. For example, there is a positive feedback loop between the birth and the population, what you can see here. Since the more births, the bigger the population is, and vice versa. On the contrary, the deaths are provoking a negative feedback loop, since while the population makes the death number to increase, the bigger the death number, the lower the population is. As a second step, once that a causal loop diagram is known, it is important then to identify from these the formal elements of the system dynamics model: the variables, the stocks, the flows, and the feedback loops. The variables, general elements affecting the process or problem; the stocks, which are accumulators of the system; the flows, making the accumulators increase or decrease; and the feedback loops which are generating feedback behaviors. As an example, for the case of the population, the stock is the variable that is accumulating a long time. That is the population here. The flows would then be the elements making this stock to increase or to decrease. That is the birth and the deaths. In this simple model, all the other variables may be identified as auxiliary, but please think that you can remain making this model bigger, better, and thus more representative of the real system. For example, considering the available resources as a stock that also accumulates and may have its own inflows and outflows. That is one way to improve this model, and so on. With the model built as a third step, it is possible then to simulate and observe the behavior of the stocks and the flows, that is, the state variables of the system. For example, in a population simulation model, it would be interesting to see how the population grows while the birth number is bigger than the death number. What you can see here, the birth number is higher than the death number. Or if these were equivalent, then the population would remain stable, what you can see here and what you can see here as well. In this example, you can see that the population starts at 10 with a stable birth and death rates. When the death rate decreases, then the number of births is higher than the number of deaths. Thus, the population starts increasing in an accelerated way. By the moment the birth rates start decreasing, then this population's growing acceleration decreases as well. The population then tends to stabilize when the birth and the death rate are equivalent, again what you can see here. So the population stabilizes. That is the general behavior of S-shaped simulated population, with the birth and the death rates as inflows and outflows respectively. What you can see here is the correspondence of the simulation model with what you have just shown here in the graph. And all these simulations for what? Here, the power of simulations. They allow us to generate scenarios and then support strategic discussions about the system that is being simulated. And all this through an inexpensive information generator, which is the simulation model. That was, in a superficial way, an explanation of what system dynamics is useful for. But what is the case of application or use of system dynamics of our interest in this video? Well, it is the software development process. We are interested in understanding the dynamics of the software development process. In the case of the Larman process, there are many elements involved in this process. Let us remember that the first step consisted of having a causal loop diagram of the problem or process. If we include in this causal loop diagram all the elements of the software process, they would probably occupy all the space and would not be enough. The main elements are considered here: the analysis accomplishment, the design, the implementation, the testing, and many other factors, as you may see: factors of personnel, factors of hardware, factors of project, or factors of software. Also elements like the complexity, like the specifications, the glossary construction, the lines of code writing, and many more. You can add as many auxiliary activities as you want. Here the glossary creation, for example, is parallel to all the other aspects of the process that have been included. And with this information, you can, at an early stage, see which of these elements are stocks, what you can see here, and which are flows. In general, to deal with complex problems, it is very useful to represent them using this. So, the software process is complex, and there are many factors affecting it. These are the variables affecting the software process. So the simulation model that you will see now comprehends three views or three layers of the model. One for representing the computation or estimation of the effort required to carry on the project. One for representing the execution of the process, so the accomplishment of the phases of the process. And one for representing the consumption of the estimated effort. In the first view, you will only see auxiliary variables representing all the factors affecting the estimation of effort required for the project. Here you see the represented factors such as the experience of the analyst, the complexity of the product to be developed, the experience of the programmer, the experience with the development platform, and so on. Here is where you can set the values of such parameters or even play with them. But all those factors are affecting the accumulations of this system. And this is represented in the second view of this model. Here the accumulations are the accomplishment of the phases of the software project: the analysis, design, implementation, or testing. Also, there is a stock accumulating but representing an auxiliary stock, the glossary terms aggregation, which is not a phase of the process but is important as well, and you can consider it. Here you can see how all the factors represented in view 1, the one that we saw before, are affecting this phase's accomplishment. These are here shown as shadow variables, what you can see here, since they were defined in view 1, the one we saw before. And the third view is representing the effort consumption within the phases of the project. Each of the phases of the process will consume resources at a determined time. Well, that behavior is represented here. It is important to note that the behavior is defined by mathematical equations that are inside the simulation elements definition. That is a task that will not be specified here. The important thing is that the simulation model now is built with the single behavior already established, so that we can now simulate and study the whole system behavior and the effect of relations and correlations. So let's run the simulation. By running the simulation, we can understand the system behavior. What is important to us is to check the analysis, the design, the implementation and testing, also the effort consumption and project costs. Here you can see the representation of the workflows of the phases of the process. You may see that the blue line, the analysis, is the first. It's the first of the flows in having a significant activity. Once that you have some of the analysis accomplished, you can now see the workflow of the design, what you can see here. It emerges when the analysis has been accomplished a little bit, and it concentrates much of the resources around the 14th and around the 14th month of the process. After that, the coding is the core workflow around the 18th month of the project, when analysis and design were mature enough, what you can see here. And finally, the testing workflow, what you can see here, has its main activity within the 24th month and the 40th month of the project. If you think about the workflow as flows helping to accomplish with the phases of the process, you can see that the analysis started to be the most accelerated phase during the first months of the project. Then, with some of the analysis done, then the design started and the implementation of the code after this. Finally, the testing was the last to be accomplished, and it was ended around the 46th month of the project, making sense with the theoretical foundations of a software process. Regarding the effort consumption, you can see first the analysis, then the design, Afterwards, the implementation, and finally the testing phase, which also corresponds with the theoretical foundations of effort consumption and software economics. And how variations in the factors that we consider for the simulation model may affect the whole system behavior. Well, let's see a few examples. Let's concentrate in an alternative scenario, okay, scenario 1, in which the team intervening in the process is efficient. In this scenario, there is an effective software development team which has certain characteristics that affect the performance and the results obtained. As they are effective, they are mainly characterized by a precise consumption of resources, achieving the objectives in a timely manner, and with an acceptable quality that is close to the expected. Effective teams are limited to achieving the objectives set without any major effort to exceed what is expected of them or to optimize the consumption of resources. They just do what they have to do. In this scenario, there is a better capability analysis. They have a better experience using the development platform. The programmers are better than in the nominal state, so also the language used is widely known. The development team is talented in managing the tools and following an established schedule. In terms of modeling, these general improvements on the factors are represented through these variations on the values assigned. What you may see is that the nominal values were set up to 1, and you can see some variations that represent this improvement in the general scenario. If we simulate again and check the effect, we can see that the workflows in general have moved to the left. What you can see here, for example, and here, for example. That is, they occur earlier in time, so implying less resources consumption and a better budget management. You can see this in the accomplishment of the phases as well. What you can see here is that the phases accomplishment occurs earlier in time in scenario 1 if compared to the nominal scenario. Regarding the effort consumption, there is a clear effect. It is evident how the effort consumption occurs earlier in time, which is in fact the cause of all the improvements on the behavior of the whole system and its specific state variables. So the stocks I mentioned before. Now, let's think about another scenario in which instead of having an effective team, we have an ineffective team, okay? In this case, in this scenario, there is a worse capability of the analyst. They have poor experience using the development platform. The programmers are not better than in the nominal state. The language used is not widely known by the programmers, and the team is not very efficient at managing the tools and following an established schedule. These variations are represented by increasing the values on the related factors. So most of them increase the nominal value, which was originally set up to 1. The effect is similar but quite the opposite than the previous graphs. Instead of occurring earlier, there is a delay effect on the occurrence of the workflows of the phases. So this delay implies a bigger resources consumption and then a harmful scenario for the software development company. This harmful effect can be generalized since the effect is also seen in the accomplishment of the phases. And what about project costs? Is there a significant variation? Well, that is what you can see here. In the nominal state, the project cost is around 100,000. In the scenario 2, which is the one in which the elements decrease, they approach the 150,000. And in the case of scenario 1, in which the factors improve, the project cost decreases to 50,000. So it is important to see these variations as well. So that was all regarding the presentation. Thank you very much for listening.